Okay, now our today's lecture is on um, two data structures, and in these two data structures we are not going to cover the implementation of these data structures because you can implement it in multiple ways, and you guys have adequate idea uh, regarding how various data structures can be programmed. For example, you know how to code linked list, how to program stacks and queues using static and dynamic implementation. You know about the implementation of binary search trees and AVL trees we did last time. So here we are going to cover two data structures because ideally these lectures should have been independent. The data structures, one data structure is tries and the other one is sets, but these two data structures, rather these two lectures are a bit small, precise ones, so I have combined them into one lecture, so that will be convenient. So it will result in uploading, it will result in me in uploading a single file as well, so maybe it's fine. So tries is a data structure which basically represents a dictionary. For example, in Microsoft Word, for example, okay, let me open some file. Uh, for example, this is a file and I write something, I am a boy, my name is my name is Alpha, and I write something like which is a spelling mistake, right? So what happens is actually internally the Microsoft Word has a dictionary which maintains a list of approved words, or list of words which are there in a dictionary of a particular language, because English has a different dictionary, French has a different dictionary, so on and so forth. So what it does, it picks a word from here and it checks it within its dictionary, and if this word is available in this dictionary, so it's okay, it's fine. But in case if a word like this one, it is not available in this dictionary, it regards this one as a potential spelling mistake, right? So instead of going into the details of this case study, we are going to look at this problem from the data structures perspective. From the data structures perspective, we need to have a data structure which is quick enough and efficient enough in terms of storage, and quick enough in terms of execution time, so that so many words can be stored in a concise or in a brief manner. So there are many options in the data structures which we can do, but tries is one of the options which is particularly designed for storing dictionary words. So tries is a special structure to represent sets of character strings. The word tries has been extracted from the word retrieval. So this tries has been extracted from here. It's a middle word of word retrieval. So from this, the data structure has been named like tries. Uh, okay, now what it does. This example, which is written on the slide, and I'm not going to read it because I've explained it to you that how it works. So it reads a file, breaks it into words, and find those words which are in the standard dictionary, and the remaining words are termed as possible or potential spelling mistakes. So how does this tries work? There are many operations in the tries data structure: insert, delete, make, and print, and so on and so forth. So to explain to you how it works, for example, I have a dictionary. For example, in the dictionary we have word sin. This is a word. Okay, other instead of keeping it case sensitive, let me make it case sensitive. There is a word in the dictionary, sin. There is another word, sing, right? There is another word, let's say some, and let's say there is a word zoo, right? Now This let's suppose that this is a dictionary which I want to store in a data structure, and I'm going to use the tries. So in a tries is basically like a tree. The root node of the tree has the value null, right? There is no value stored in the tree. Considering English as a language, so the values which can be stored in the node are A, B, C up to Z, right? Uh, and there is another value which can be stored, that is a special character $, right? So these are possible values which can be stored in a node, right, for a language which consists of English characters, right? So let me draw the tries data structure for this particular set of words which makes up a dictionary. So the first word is sin. So what I will do, I will write S here, right, and the next character is I will write I here, next child, and the next child is N, I will write N here, and then this word ends, so this is N, right? Since it is ending, so to demonstrate or mark the end of a word, I will be putting a special character $sign here, right? So sorry, I have successfully saved the first word in the dictionary, which is represented with the tries data structure. Now the next word is sing, right? So I will start from the root. If I see S is already saved here, so I am not going to do anything. I will go down and I will see I is already stored here, so I am not going to do anything. Now I come down here and N is already stored here, I am not going to do anything. But G is not here, so I will make a new child of this node N and store G here. And after that this sing ends, so after this G I will be putting the $, $sign, right? So this is this word is also saved. Now the third word is sum. So I will start from the root. Null is there, S is already saved. I will go down, but if I see here I is stored here, so this U may be somewhere down the stream, but since immediately after this S I require U, which is not available, so I will be making a new child of S with the name U, and then after this U I have to store M, so I will be storing M, and after this M there will be a $sign which will indicate. This $sign is basically a special character. You can use any other special character for this, right? So I have stored sum as well. Finally zoo, I need to store zoo here, so I will start from the root node, but there is no node here with the name with the value Z, so I will have to create a new node Z, and then there is an O, and then there is another O. Since we need to have an O after this O, so this single O won't count, so we will have another O, and after that this word ends, so I will be putting a $sign here, right? So this is how the tries data structure is implemented. Now one thing which you will notice, that how many child a node can have. Just think about it for a while, how many children a node can. For example, in a binary search tree, or for that matter a binary tree, each node can have a maximum of 2 child, right? If same goes for AVL trees as well, each node has a maximum of 2 child. But here in tries, in TRIES, how many children a node can have. Now if you see a node can, for example this null, for example rather this S can have A after this, it can have B after this up to Z. So this node can have 26 children, but it can also have this special character as well, this $sign, so 26 plus 1. So each node can have a maximum of 27 child here in the tries data structure, right? Now let us go back to the slide just to make sure I did not miss anything. So tries are appropriate when many words begin with the same sequence of letters, because you end up conserving a lot of space due to that. So when the number of distinct prefixes among all words in the set is much less than the total length of all the words. Each path from the root to the leaf corresponds to one word in the represented set, where if you notice, the leaf is represented by a node having $sign, right? Nodes of the tries correspond to the prefix of word in the set. Now if you see here, this is a dictionary of words: the, then, thin, tin, sin, sing, so on and so forth. And here it's already mentioned that each node can have 27 children, from A to Z 26, and $1. That's all. So this was quite brief, this tries data structure. So visually it is shown here. The one I showed you on the screen, I stored the values in the node, but here for the sake of demonstration the values are shown on the edges. Otherwise these values are actually stored in the node itself, right? And the root node always contains null, because if, for example, if in a tries I make a try here and in the root node I store A, it means that all the words represented by this tries data structure are going to start from A. So that is why if we start it from null, so we can have child A, where following this child there can be words starting from A. We can have a child B, where the nodes following this child can represent words starting from B, so on and so forth. So that is why we do not restrict the root node of the tries to a particular character. We always place null in the tries data structures root, right? Okay, but again, this you can think about its implementation. It can be implemented in many ways. The most inefficient way to represent tries is to make a node, structure node, having 27 or 28 pointers. But that is quite inefficient implementation. But there are other implementations that you need to think about. Now the next data structure which we are going to cover is the sets. Now if you recall sets, okay, let me try to draw it for you. I don't know it will work. Okay, wait a second. For example, if we have a set named set u, which is equal to a comma b comma c, so this is a set, and we have another set x which is equal to c comma d, right? So we are talking about such sets, and rather I should have named this this set u as something else, because now I'm going to, okay, let me use another operation. For example, if I say x intersection u, so the resultant set will be the common values between set u and x, and the common value is only one, which is c. So this is the resultant. So we are talking about these sets here. Now how can we represent these sets in the memory, right? So again, like many other implementations of various data structures, here we also have static implementation of the sets and dynamic implementation of the sets, right? Again, let me go through these slides. There is no code here, but it is expected that you will be able to code such programs, maybe in your exams or assignments or quizzes. Now, coming back to what I was saying, is the static implementation of sets. Now in the static implementation, what we can do is that, for example, I have a set as the universal set, which has the value, let's say 1 comma 2 comma 3 comma 4 comma 5, okay, this is NF, and then I have a set A, which is that has a value 1 comma 4, right? And then I have the set B, which has the value, let's say 4 comma 5, right? Now when in the static implementation of these sets, I can use bit vectors. What I can do, I can declare an array int u of size. What is the size of this universal set? 0 1 2 3 4, like it has 5 slots, right? Now this is the set which will represent the universal set, but here, since we know the size of the universal set, so intelligent approach will be not to declare this set. What we can do is that instead what we can do is that we can declare an array named A of size 5. We can declare another array of named B of size 5 as well, right? Now in the array A, we will have 5 cells, right? Cell 0, cell 1, cell 2, cell 3, cell 4, cell 5, right? Now this 0 will correspond to the first value in the universal set, this 1 will correspond to the second value in the universal set, so on and so forth. But you can make your life convenient as well in a different manner. For example, instead of making the array of size 5, you make the array of size 6, right? You make the array of size 6, 6 slots, and you always ignore the 0th slot, right? You don't use it at all, right? Now if you see set A, in the set A we have value 1, go to the index 1, turn it on. In the set A, the value 4 is there, go to the index number 4 and set it on. Now turn off rest of the values. Same goes for the set B. In the set B as well, don't use the 0th slot, right? If you see here, 4 is available in set B, so go to the 4th index, turn it on. 5 is available in set B, go to the 5th index, turn it on, and turn off rest of the indices, right? So this is how you can store sets in arrays using bit vectors. So this is static implementation of the sets, right? So whatever I explained here is already written in these slides. I will be shortly uploading these slides on the CMS as well. Now keeping the implementation which I told you earlier in mind, if you want to see if a value is available in a set or not, if you want to insert a value in the set, or if you want to delete a value in the set using the bit vector representation, so we simply need to go to that particular index, index 0, 1, 2, 3, 4 and 5. We simply need to go to that particular index. If you want to see membership, then we need to check if it is on or off, right? If you want to insert, simply go to that index, turn it on, like write 1 there. If you want to delete it, go to that index, turn it off. So all these operations, membership operation, insert and delete operation, these are performed in order of 1 execution time. And if you want to perform union and intersection operations, you are simply going to apply and or gates on these arrays. So that can also be done, but it is not going to happen in order of 1, because you will need a loop from 0 to n. For example, n here is 5, but n can be any number. So those operations can be performed in order of n time using the bit vector representation of the sets, right? So this I have explained it to you. Right, the universal function may not always be consecutive numbers. For example, here what I considered the universal set was consisting of 1, 2, 3, 4 and 5, but maybe at times universal set is like a 6, 7, so on and so forth. In that particular case, you need to have a translation function or mapping function that can translate the value a to the slot or index in an array. So in that case, all the operations which I told you earlier, these may not be performed in order of one time, but if the universal set is of consecutive natural numbers, then yes, the insert, delete and membership function can be executed in order of one time, and union, intersection and difference operation on sets can be performed in order of n time, right? Now, there is another implementation of the sets, which is called the dynamic implementation of the sets, and of course the dynamic implementation is always done using linked list based implementation, right? So in the dynamic implementation of these sets, instead of okay, let us try to do that. For example, we have a here I am not going to write the universal set, because all we already know a is equal to 1 comma 3 comma let's say 5. These values are in set A, and B, let's suppose we have values 1 comma 4, right? These are the values. Now and the universal set may be of let's say from 1 to 5, but here we are using the dynamic or linked list based implementation. So what we will do, for the set A, we will make a linked list having 3 nodes, and the first node will have value 1, the next node will have value 3, and the next node will have value 5. Similarly, the linked list B will represent the set B having value 1 and having value 4 in the last node, right? So this is how, if you see here, this this implementation, linked list implementation may not be very time efficient, but it is saving a lot of space, whereas the bit vector representation was very much time efficient, but it was consuming a bit of space, because if in a set we have only one elements, but we will have to create an array equivalent to the size of the complete universal set. So the bit vector implementation was consuming space but conserving time. So as I told you, there is always a trade-off between time and space. Whenever you try to consume less time, more space is going to be occupied, and whenever you try to conserve space, you may result in consuming more time. So again, coming back to what I was saying, this is the linked list based implementation, and this is how it works. Explanation is there on the slides. Okay, let me read it out for you. The items on the linked list are the members of the set. Linked list uses space proportional to the size of the set represented, not the universal set. And the linked list can represent the sets where the universal set is infinite. So this has an advantage, because if the universal set is infinite, you cannot go for the bit vector representation. Right? Now, insertion of an item in a linked list based representation of set. So when the list is unsorted, right? So sorry, it's not insertion. I'm sorry. This is intersection. So there are two lists, and we want to have an intersection of these lists. For example, set A has 1, 2 value, and set B has value 1, 2, 3 and 4, and we want to have an intersection of these sets. And in the intersection, we know that we need to make sure that whatever is common between these two sets is to be stored in the third set. So this operation, of course, you will pick one thing from here and you will check it in the complete set, second one, and if it is there, you will store it in the A intersection B. Sorry, this mouse is not supporting me, so I'm not very much good at writing here. Then you will pick the second value from this first set and you will go through the entire second set. So all this operation is going to consume order of n square time, provided these lists are unsorted, right? By chance I've made them sorted here, but in case these lists are sorted, then the operation cost is a bit decreased. Similarly, if you want to assign one list to another, so copying is easy. You just need to make changes in the heads of the linked list. That will be convenient. Union is also sort of convenient, but it will because it's not like that you will pick the head of one list and placing it to the tail of the list, because this can result in duplicate values, right? So you need to remove that as well. So in the sorted list this may be easy, but in the unsorted list this operation may require order of n square time. Similarly, the operations like finding minimum from the list, finding an element in the list, deleting and inserting an element in the list will require different execution time and different sort of functions in the dynamic implementation of the list. So that was all for the two data structures which we covered, and the code I have not mentioned here because you need to do it yourself, and I'll be giving you maybe a quiz or maybe an assignment on this, most probably, but I will let you know by email what we do, because I feel like you need to do an assignment on evil trees, and maybe questions like this, insertion in the sets or deletion in the sets can be covered in quiz as well. So that's all. Thank you.